Welcome to this video lecture. My name is Mark Scythian. The date today is June 27, 2022. This lecture is titled How to Calculate Piston Engine Brake Horsepower Using Just Displacement and RPM Setting. So assume we have a 4-stroke, 6-cylinder, 3.6 liter automobile gasoline piston engine operating at 3,400 RPM. Modern automobiles manufactured after 2008 or fourth generation automobiles ingest air into their cylinders at 100% volumetric efficiency based on the variable valve camshaft timing without the need of a turbocharger. So the displacement charge of air is equal to the displacement rating of the engine, as opposed to the older third, second, first generation cars, which without a turbocharger, naturally aspirated piston engines would ingest about 80% volumetric efficiency charge and a 3% loss of brake horsepower every 1,000 feet above mean sea level thereafter. And we have a default air-fuel ratio for gasoline combustion at 14.7 to 1 with all electronic fuel injection types since about 1983 to the present. Energy density of gasoline, 20,000 BTU per pound. There's 1,056 watts of thermal power per every 1 BTU per second heat output. We'll use a no-load brake thermal efficiency of 33%. Then we simply just convert the liters displacement into cubic inches, and then convert the cubic inches into cubic feet cylinder displacement. Then compute the atmospheric pressure based on the altitude or the elevation above mean sea level. Also recording the air temperature so that we can then compute the air density. So we're working with a 4-stroke, 6-cylinder piston engine, so every power stroke, 2 revolutions of the crankshaft will occur. So at 3,400 RPM, there's 1,700 power strokes per minute, or 28.33 power strokes per second. So that means there's also an equal number of compression, intake, and exhaust strokes. So we have 28.33 intake strokes per second. Then we simply multiply the cubic feet displacement times the intake strokes per second to yield 3.6 cubic feet per second air intake into the cylinder. Then we multiply that value times the air density. So we can compute the pounds per second mass airflow entering the engine at 3,400 RPM. Then we divide that by 14.7 to compute the gasoline fuel consumption per second, pounds per second, so 0.0177 pounds per second gasoline fuel consumption at 3,400 RPM. So we have the thermodynamic constants for the fuel and the heat rate. So the total input power in the form of burning gasoline is about 373.5 kilowatts, then multiplied times the brake thermal efficiency of 33%. So we have approximately 123.2 kilowatt, or 123.3 kilowatts of available power at the engine's crankshaft as in mechanical power. 746 watts per horsepower. So when we divide it out, the approximate calculation just from having the displacement and RPM setting is 165 brake horsepower at 3,400 RPM. So to test and check how accurate this calculation is, we can use the Planck over 33,000 formula. We first start by computing the brake mean effective pressure during each power stroke at 3,400 RPM. And at 3,400 RPM, this particular engine has 272 foot-pounds of torque We divide that value into the cubic inch displacement times 150.8 to yield 186.7 psi brake mean effective pressure during each power stroke at 3,400 RPM. So if we work the formula out, as in P for brake mean effective pressure in PSI, L for piston stroke length in feet, bore cross-sectional area, pi r squared times pi r squared of the bore diameter, piston stroke length in feet, and the stroke inches divided by 12, number of power strokes, and then number of cylinders divided by 33,000, the number of foot-pounds per minute per horsepower. Since we're using RPM, we use 33,000. It's 175.6 brake horsepower. So this method of calculation is 94% accurate. So if we use another scenario, a two-stroke gasoline piston engine, let's say powering a string trimmer or chainsaw, let's say it operates at 6,800 RPM and has a total displacement of 25 cc's. We can use a volumetric efficiency of 80% because it's just a naturally aspirated small engine without any automotive technology on board. And so we identify it's a two-stroke duty cycle, as in 3 events happening on the downstroke, 1 event happening on the upstroke. Of course, we're using the two-stroke gasoline. It's a mixture of 4 ounces of two-stroke oil per 1 US gallon, so 32 to 1. Two-stroke gasoline mixture. So we have slightly richer mixture, even though it's not EFI, it's just carbureted. We still run about 14 to 1, slightly richer. And same air temperature and elevation. So we compute 1.53 cubic inches displacement. And of course, the number of power strokes per minute in a two-stroke piston engine is equal to the RPM. So that means we're having 113.33 power strokes per second at 6,800 RPM in this two-stroke single-cylinder piston engine. So really, we have an air charge that's at 80% of the cubic inch displacement. So at the summation of the power strokes per second, we have 138.72 cubic inches of air intake per second at 6,800 RPM. So we convert that value into cubic feet at cubic feet per second air intake at 6,800 RPM, 0.08. And again, we have the same air density. And then the mass airflow entering the engine at 6,800 RPM is 0.00576 pounds per second. We divide that by 14, 0.00041 pounds per second, two-stroke gasoline consumption. And of course, the naphtha, two-stroke oil, lubricant additives do not affect the energy density of the gasoline because its energy density is absorbed by kinetic friction. The fuel is used to lubricate the engine in a two-stroke before it's drawn into the cylinder, compressed and fired. So 20,000 BTU per pound still. So we work this out, we get 3.5 brake horsepower at 6,800 RPM. And of course the torque value as well. These are the this method of calculation. So now we can check the specs on this actual engine. It's actually 3.7 brake horsepower and 2.9 foot-pounds torque at 6,800 RPM. So again, it's about 93 to 94% accurate if we use the discernment for the type of engine. In this case, a two-stroke small engine. And note that the BMEP coefficient for two-stroke piston engines is actually 74.5, 1/2 of what it is for a two-stroke, 150.8. So the rule of thumb on a four-stroke piston engine, if you are developing 1 foot-pound of torque per every cubic inch, then the BMEP is 150.8. That's on a four-stroke piston engine, and it's exactly half that in a two-stroke, 74.5, at 1-to-1 ratio between torque and cubic inch displacement. Thank you for watching this video lecture, and have a great day.